I'm Andrea Cromera, and this is the second lab report for Physics 2211. This presentation can be broken up into the following 5 key parts. So to introduce, the purpose of this lab is to understand the physics principles behind the motion of a ball falling from rest. To help understand the motion, we must understand the forces acting upon it through the use of computational modeling. And the results will show that the computational model, which includes the drag force and gravitational force, is actually accurate and closer to the observed data instead of just considering gravity acting on the system. In this experiment, we must understand 2 physics principles. First, Newton's second law, which states that if an object has a net force acting on it, it will accelerate proportionally. Momentum is the quantity of motion in an object, and together these principles relate to the net interaction between system and surroundings to the observed motion, meaning the changes of momentum in the system, otherwise known as the momentum principle. And lastly, net force is simply the vector sum of all the forces acting upon the system. Newton's second law can be described using the formula force equals mass times acceleration, but with algebraic substitution, we can make it equal to change in momentum divided by change in time. And then momentum is mass times the velocity vector. This figure shows a clear depiction of Newton's second law with the free body diagram, where we can see that initially only its weight is affecting the system. However, as velocity increases, drag force also increases and eventually becomes equal to its weight, which means that the object will eventually reach its terminal velocity. However, that is a subject we will touch later. Moving on to the actual experiment. This video shows the motion of the ball with the aid of tracker. Then I plotted the graph of its position versus time, which we can see that the ball falls to the surface straight down. And I set the axis to indicate that the initial position of the ball was positive, and as it fell, it moved towards the negative y direction. So for the computational model, I used a base code adhered to the assignment, which is this. The ball mass was 1, and then the position vector was the data from tracker. The initial velocity was 0 because it fell from rest. Delta t was calculated by taking any 2 time intervals and taking its difference. And lastly, this is a no drag model, so b is 0. I used the following formulas for the iterative part. This is the position and the velocity update formula. Then the net force, since we are only considering the force of gravity, it's equal to negative mass times gravity times j hat, because it's moving in the y direction. Then this is the code, and we can see where I included the force of gravity, the velocity update, and position update formulas. And these are the results for the no drag model. To calculate the drag force, I used the following equation, and the net force became the vector sum of gravity and drag. This is the actual code for the drag inclusive model, where b was 0.45, and the net force was its weight times the drag force, which is this equation. And these are the results for the drag inclusive model. I moved on to compare the observed versus predicted data in the following graph. This figure shows the position versus time with both the observed data from tracker and predicted data using GlowScript. The 3 data sets are fairly similar. However, the computational model with no drag shows a steeper, more negatively inclined slope than the actual observed data. The model, which includes drag, has a steeper slope, but has closer endpoints to the observed data, which indicates that when we include all acting forces on the motion of a system, the model is closer to the observed data. So if we move on to the reflection, first let's consider, what does this mean? If we compare the velocity time graph for the 2 models, we must consider the terminal velocity. The graph on the left is a model for no drag, a negative slope, but straight line showing no acceleration, meaning that no specific speed can be reached. The graph on the right, which includes gravity and drag as forces acting on the ball, does show that a specific speed, otherwise known as terminal velocity, is reached, meaning that eventually drag and the ball's weight become equal in magnitude in a system moving at a high velocity. Then let's consider, what if the ball was thrown downward? instead of falling from rest. The terminal velocity would still be reached, but maybe in less time, even though both forces being taken under consideration, they would come to an equal magnitude, meaning that drag and weight would become equal. Lastly, let's consider the errors. First, we're assuming that the object fell from perfect rest, meaning that it had no motion in the beginning, which is something we can be super certain of. Then the accuracy of the initial conditions in the model, in which we are assuming that the ball is a perfect sphere and a point mass. Thank you.